In order for us to sketch a graph of a rational function, we need to find this information: the intercepts, the asymptotes, and the removable discontinuities. The intercepts are going to be points that are labeled as ordered pairs. The x-intercepts come from the x values that make only the numerator of the function equal to 0. And the y-intercepts come from the result when you substitute 0 in for x. Vertical asymptotes are the graphical representations of the essential discontinuities, and they come from the x values that make only the denominator equal to 0. On the graph, they're going to look like vertical dotted lines. The horizontal or oblique asymptotes are the graphical representations of the end behavior, and we get them from the results of the long division without using the remainder. They're also going to be graphed as dotted lines, but they might be diagonal lines, horizontal lines, or they might look like some other function like a quadratic or a cubic function. It all depends on whatever the result of the long division is. And then the removable discontinuities are graphed as open dots. They're also called holes. And they come from the x values that make the numerator and the denominator equal to 0 at the same time. So in other words, they come from the factors that end up getting canceled. So let's look at our first example here. First of all, there was a typo on this example that 3 at the end of the numerator is supposed to have an x attached to it. First, we'll find the y-intercept by plugging in 0 for x. That gives us a result of 0 over negative 2, which simplifies to just 0. So our y-intercept is going to be at the origin. Next, we'll figure out what the factored form is so that we can find some of the rest of the information. Looking at the x-intercepts, we want to figure out what makes just the numerator equal to 0. So 0, 0 would be one of the spots where that occurs, and that comes from this isolated x out in front. And then the other factor that's in there, x squared minus 2x plus 3, there are no real values that cause that to equal 0. So this function is only going to have one x-intercept. That comes from the x factor, the isolated x factor that is out in front in the numerator of that fraction. One way that you can check to see that x squared minus 2x plus 3 doesn't have any values that make it equal to 0 is by graphing it. You'll see that graph does not cross the x-axis. Next, we'll find the essential discontinuities. That comes from the x values that make only the denominator equal to 0. So in this case, that would just be at positive 2. And since there were no factors that canceled, this one has no removable discontinuities. Last, we'll find the end behavior by doing long division. Looks like our result is a quadratic function, x squared plus 3. Now that we have our intercepts, our asymptotes, and our end behavior, and our removable discontinuities, we're ready to sketch a graph. I'll label the ordered pair first. That's both our y-intercept and our x-intercept. Next, the essential discontinuity will be labeled as a vertical dotted line where x is equal to 2. There are no removable discontinuities to worry about. So last, we just need to sketch the end behavior, the function y equals x squared plus 3, which is just a basic quadratic function that's been shifted upwards 3 units. Once you get to this point, I would not expect you to know where the actual location of the function is without using your graphing calculator. So I took a look at the graph of this rational function and saw that the location of the curves were in 2 separate locations. And that's it. That gives us a sketch of our rational function. You can see I'm not real picky about labeling tick marks or labeling scales on the graph, as long as you label the actual information and the location of those pieces of information makes sense relative to each other, so that the graph takes on the shape that it's supposed to take on, then the labeling will be sufficient. Let's take a look at one more example. Again, we'll go ahead and get the factored form because a lot of the information that we look for is easier to find from the factored form. I'll get the y-intercept first by plugging in 0 for x. That gives us 0 over 15, which just simplifies to 0. So our y-intercept is at the origin. Next, I'll look for the x-intercepts. It's the values that make just the numerator equal to 0. So one of the values will be at 0, the other value will be at -1. Again, that comes from these factors here. 0 comes from that factor, -1 comes from that factor. Essential discontinuities are next, and it's the values of x that make only the denominator equal to 0. So that's coming from the factor that does not get canceled. Then the removable discontinuities, this time we do have some factors that cancel. It's x minus 5. So positive 5 would be the x value of the removable discontinuity. Now the removable discontinuity is graphed as an open point. So in order to find the y value of that point, we need to take our value of 5 and plug it into the simplified version of the function. So here's the simplified version of the function. It's what's left over after we remove the common factor. And then we'll plug in our value of 5 for x. That gives us 30 over 2. So the y value of our removable discontinuity is 15. Last, we'll find the end behavior by doing long division. Looks like we get the linear function y equals x plus 4. Now that we have all of our information, we're ready to graph. We'll graph the intercepts first as points and label them with their ordered pairs. The essential discontinuity will be labeled as a vertical asymptote, a dotted line at x equals 3. Our removable discontinuity will be graphed as an open dot at the point 5, 15. And then our end behavior is going to be the linear function y equals x plus 4, which is just the basic linear function that's been shifted up 4 units. And again, at this point, I wouldn't expect you to necessarily know where the curve should be, although based on the information that's graphed, in order for this to make sense, there's only one possibility for the curves, and that's down here and up here. But again, you can graph that in your graphing calculator in order to figure out where the location of those curves should be.